Okay, hi everyone. Again, my name is Sylvester Orimaye. I know I'm not new to the majority of you. So today I'll discuss about one of my research contributions. First, I work on Alzheimer's disease. I apply machine learning techniques to detect early onset Alzheimer's disease. So today I'll talk about how I've used machine learning and natural language processing to detect early onset Alzheimer's disease. So I wanted to start with a little bit of research background. Alzheimer's disease is it's one of the leading causes of dementia, and as a matter of fact, it is the sixth leading cause of death in the United States. So this is a chronic disease that really needs our attention. And as the aging population continues to grow, we're going to continue to have prevalence of Alzheimer's disease. So the image you have before you, it's showing what we call the Alzheimer's dementia continuum. So you have a cognitively healthy human, and at some point in their lifetime, they progress to dementia. So what goes between being cognitively healthy and having dementia at some point? So we see people progress from cognitively healthy status to mild cognitive impairment, and then they progress to what we call Alzheimer's disease. And even within Alzheimer's disease, you have two different categories, which is possible Alzheimer's disease or probable Alzheimer's disease. And then you ultimately move into dementia. More recently, I've been working on influencing this continuum by introducing depression as a component within the pathway. So we've seen link between depression, especially severe forms of depression, progress to Alzheimer's disease later in life. But more to come about that. So what I'm trying to do here is to interject this continuum and see, can we detect people who might have Alzheimer's disease later in life? Can we detect them early enough using machine learning techniques? So would somehow be predicting, for example, mild cognitive impairment. So if you can detect people with MCI, then you're likely to reduce the number of people that would move on to dementia later in life. Sorry, I'm clicking my slide. Okay, that moved. So I've actually talked a little bit about, AD being the sixth leading cause of death in the US, but I also wanted to mention that up until now that we have what we call PET, amyloid PET imaging or scan, the main form of detecting cognitive impairment or Alzheimer's disease has been through what we call neuropsychological examinations, such as the mini-mental state examination or MOCA. So what we're trying to do is to automate the process. So if we are able to use automated machine learning techniques, first we will not only increase accuracy, but we're going to have to, we'll be able to do what we call large-scale screening, especially among rural populations where it is very expensive to have access to PET scan, or it's even difficult to reach those populations. For example, I used to work in the Appalachian region of the United States, where you have remote locations that folks over there hardly come to the metro area to seek healthcare. So if we had a way to do telemedicine backed by machine learning technique, you could remotely access that population and screen them for the possibility of early onset Alzheimer's disease. So what I've done is to propose a machine learning based diagnostic or assessment tool for detecting the disease. So, and I published this in 2020. So there are a lot of ways you could do that using machine learning techniques, but what I've used is actually speech samples. So I focus on using verbal utterances. So when you interact with some sort of stimuli, and then we record your speech, we are able to use our machine learning algorithm to analyze patterns from your verbal utterances, and then learn from that to predict others that might have similar condition. Right, so it is a combination of what we call natural language processing and deep learning. Deep learning is one of the famous techniques in machine learning these days, and we're going to talk a little bit about that. So combining those two aspects of artificial intelligence, we're able to develop the algorithm and also created a tool to help us do the screening. So I've actually introduced several forms of these techniques, but I'll go through one of them. So I've introduced, machine learning techniques that use something other than deep neural networks. But in this particular case, I'll show you what we did differently, especially something that is similar to what we are all talking about now, which is the Chat GPT. So just for context, I did my PhD. I completed my PhD in 2012, and I worked the stage in 2013. And that was when we were introducing what we call language model. So language model is something that that we use to understand, I would say, the meaning behind a document, the language space that is contained within a particular discourse, for example. So when I say a document, it could be like a page that you are describing. It could be a comment from someone. It could be a verbal discourse from a patient, right? So you want to understand the language model behind that discourse. So that's what I focus on specifically. So some people have already worked in this area. They've introduced what we call deep neural network model or neural network language model to want to solve the problems around, especially in natural language processing. They want to use language model to solve machine learning problem. So what I did was to improve on that model, by including additional techniques that I think would make sense. So this is one of those works in natural language. In neural network machine learning technique, there are several ways you could, customize your architecture to give you better performance, to work well on the problem that you're trying to solve. But before I go to this, let me quickly fast forward to what a neural network looks like. So in neural network, you have a set of inputs, because what we're trying to do here is to sort of emulate how the brain works, right? But we are nowhere near, how the brain works. But for a neural network, just a quick overview, you have a set of inputs, and then you have what we call hidden layer, which is something, which is usually in between, and most people call this the black box, right? Because you don't know what is going on within the architecture. And then after the hidden layers, you have the output, which sort of classifies your your cases, or differentiate between your cases and control, if you may. So in this diagram, you see that I call the X. Those are my inputs, and the inputs will be your variables. For example, in this case, I have a lot of what we call n-gram models, which are language models, like words from from a document or a set of verbal utterances from a particular patient or from a group of patients, right? So, and once I get the inputs into my network, I try to find dependencies between those inputs, and I learn from those dependencies to classify whether someone belongs to a case or to a control. So that is basically what a neural network is. Now, we have different forms of neural network. We have some types of neural networks that will be useful for image classification. We have some that will be useful for sentence classification or natural language processing problem. In this case, this is related to natural language processing. I'm sure you must have heard about convolutional neural network, which is specific to image. We also have recursive neural network, RNN, which is specific to natural language processing. All right. So more recently, we have what we call transformers, right? And that's a different ball game. And that one focuses on encoder and decoder mechanism within the architecture. So, but this is the simplest form of what we call multi-layer perceptron, a form of feed-forward neural network, right, in machine learning. So I'll go back to my technique. So what I've done here is to try to increase those hidden layers as one technique, and also experiment with higher order language models. So the lower level language models are usually what we call unigrams or bigrams. And many people have used this in their work, to even in medical or clinical research as well, to read medical notes, for example, clinical notes, for example, to identify particular medication or adverse medication reactions or things like that. So what I tried in this technique is to experiment with higher hidden layers, higher number of hidden layers, and also higher numbers of n-grams. So in this case, I tried up to 6 grams. So we have unigram, bigram, trigrams, and even you can decide to have a higher number of those n-grams. So how did we collect the data? I'm not sure if any of you is familiar with what we call the Boston diagnosis for aphasia. It is a kind of instrument that you use to get patients to interact, and while they're doing that, you're sort of recording their interaction, and then that gives you an opportunity to go back and examine, are they cognitively healthy or not. So in this case, we have a data set that contains Alzheimer's disease patients who we recorded, they recorded their speech samples, and then we have a set of control people who did not have Alzheimer's disease. They recorded their speech samples, and then some people manually transcribed those interviews, and then made it available for people to work with. So that was what I used. So I developed a sort of program to extract several features from those transcripts, and that's what I provided for my neural network to learn from. So this is an example of that. I mean, this is the picture that we used in that particular data set. So for me to sort of check whether what I proposed is better, I had to benchmark against some existing work in this field as well. So I implemented some of those baseline work, and then I compared my technique with those, and then check what the gain that I made was like. So for neural network or machine learning, technique that you're proposing, especially if it has to do with, clinical research, one way to measure the accuracy or the relevance of that tool or the model is to use area under the curve. Usually, if you are anything above, 80%, will be deemed, relevant in clinical research. But of course, the higher, the better, because you're dealing with, people's health, right? And because we're using language model, we use what we call perplexity to measure how good, how relevant is the language model. So from the word, perplex, for example, surprise. So in language model, if your model is not able to pick something extraordinarily, then you will say your model is not really perplexed about it, right? But if your model is able to catch, some unique patterns, and then you say, oh yeah, I'm perplexed by that. I'm surprised I can see this pattern, right? So, but again, the lower your perplexity, the better your model will be. And obviously, you want to reduce the error of the machine learning model as well. In this case, the neural network. So if you're looking at the error and the error column, you see that we are trying to reduce that error. So compared to the baseline methods, the ones that the two lower models, the technique that I proposed actually reduced the error much more than what you will see in the baseline models. We did one for the mild cognitive impairment group. We also did one for the Alzheimer's disease group. What we noticed though was that it is far easier to detect people with Alzheimer's disease because it's already, when they have the disease, you can already tell from their speech, right? Because they are already they are almost reaching that demented stage. So you have them, you see them struggling a lot, to formulate ideas, to interact with the stimulus. So, but one thing that we've done really well in this particular study is to detect mild cognitive impairment, which is very close to control. It's very close to healthy cognitive. I mean, people who are cognitively healthy, right? So, and it's another thing that we also see in this particular technique is that we are able to use this on a very sparse data set. Now, when people interact with the stimulus, they don't say a lot. So you have maybe one or two sentences. And the beauty of language model is that you can, expand those one or two sentences into a lot of features, right? Using the smallest component of your language model, like the unigrams and the bigrams or even skip grams. So that worked really well, and we also have some graphs to show, how those models perform. So what you want to see here is to see which of the lines is kind of, I would say, approaching minimum compared to others, right? So we're looking for where we can minimize the error, for example, and we're also looking for where we can minimize the perplexity. So across all the graphs, we're kind of looking for the model that we proposed, which is the one with the higher order language models, the 5N and the 4N. We see those models perform really well compared to the baseline models. So in terms of, I talked about AUC. In terms of AUC here, we'll see that those neural network model with higher order n-grams perform really well when we compare to other models. So what I just wanted to emphasize here is that language model as a way of training your machine learning model, it's really effective, and that's what we are seeing right now with ChatGPT. So the mechanism behind ChatGPT is language model, and it's based on what we call n-grams, right? So, and I mentioned that in 2013 we didn't know that ChatGPT was going to come, right? And we're kind of pushing language model, and we're struggling to explain to people what it means, what language model means. And 10 years later, it became part of what everyone would use. And so I'm just kind of telling you that when you hear about ChatGPT, the mechanism behind it is language model, and it's nothing short of what we call n-grams, right? And you can have different forms of that. You can use that to train your neural network model, and in turn, your neural network model will learn the patterns within your data sets and use that to classify whether an observation is a case or a control, or a disease or healthy, whichever way you can interpret that. So I'll just quickly talk about the limitations and conclusion. So one of the limitations here is that we had to use a particular stimulus, right? Which is that particular cookie theft image that I showed you. And when you collect your data based on that particular stimulus, your machine learning can only work on future observations that interact with the same stimulus. So if you happen to use another image called going to the market, so there could be some it may work, but it's not going to be as effective as the patient interacting with the same stimulus that you used when you were training the model. So that's why in machine learning, how you train the model matters. So, and you must have heard about diversity in machine learning or in training. You want to make sure that you collect data that is representative across different groups, right? So you don't collect data set on Caucasian and then you test, on Asian and hoping that it should work, the same way to work on Caucasians. Right. So in this case, the limitation is that this data set was collected based on that particular stimulus. If you're going to use this same model, then you have to get a patient to interact with the same image as well. Right. And as at the time we're doing this experiment, we had issues with training time, but then GPU came, cloud computing came, and it's no longer an issue anymore 10 years later. Right. So just the conclusion, there is a possibility of, training machine learning model on even sparse clinical data set. And when I say sparse clinical data set, I mean data sets that are not necessarily a lot, especially, for example, clinical notes is a good example. So, they are usually very short. And some people will say, oh, if only I can have like a page or like 2 pages of information, that will help me train my model better. But there are techniques in NLP, in machine learning, that you can use to train your model even more effectively on sparse data sets. So that's a little bit about what I've done in terms of machine learning and clinical research. I'll open the floor for questions and we can take it from there. Thank you.